In this video, we're going to take a look at the Small K Approximation. It's a lovely tool that makes our lives a little bit easier when we're trying to figure out the equilibrium concentrations using ice tables. It's a nice way to let go of that quadratic formula, which can be a little bit annoying to write sometimes. So let's take a look at an example. Here we have 0.00100 moles of water vaporized in a 2-liter flask, and it becomes hydrogen gas and oxygen gas. What will the resulting molarity of H2 and O2 be? So essentially we're asking you for what are the equilibrium concentrations. So in general, what you would do is you would make a ice table. It's an equilibrium. Like that. You'd write your ice over here. You started off with and this is in moles per liter. So your concentration is N over V, which is a 0.001. I'm not putting all the zeros after. Moles over the 2 liters. And the reason is I'm just dealing with sig figs at the end. So 0.001 divided by 2. And I get this 0.0005 moles per liter, or molar. So 0.0005 molar. I have 0 of this and 0 of this. And my change is minus 2x over here because I'm losing water. But I'm producing hydrogen and oxygen. So essentially plus 2x over here and plus x over here because it's based on my molar coefficients. And so my overall equilibrium concentrations would be 0.0005 minus 2x. This would be 2x over here, and this would be x over here. And remember, you're given the K value over here. So K for the reaction is 6.2 times 10 to the power of negative 15. And so you would solve for x by creating an equilibrium expression. So to do that, I'm just going to carry that over here. So we would do step 2. K is equal to concentration of H2 squared times O2 over the concentration of H2O squared. And then you'd plug in all your numbers. So you'd get essentially 6.2 times 10 to the power of negative 15 is equal to, okay, so we have H2 squared. So this is 2x squared times x over the 0.0005 minus 2x. And this looks like a lot. So this looks like a lot to try to solve. Oh, and sorry, that's squared as well. So when we do this, if you want to simplify things a little bit more, that could lead to, so 6.2 times 10 to the power of negative 15 is equal to, okay, 2x squared is 4x squared times x, which is 4x cubed, over 0.005 minus 2x squared. I cannot square both sides, square root both sides, because I have cubed on top and square at the bottom, so that won't work. And in this case, I can't really use a quadratic formula because I have a 4x cubed on top. So sometimes we want to be able to solve this in a simpler way, and one thing we can do is use what's called the Small K Approximation. And so here's what I want you to notice. This here, this K value is a very, very small K value. Remember, when you have a K value that's less than 1, your reactants are favored. This is much less than 1, much less than 1. So your reactants are definitely favored. What that basically means is that at equilibrium, you have more reactants than products. So it's almost as if you you didn't lose much reactant. You did lose some because you're producing some product, but it's almost as if you didn't lose much because your reactants are so much more favored compared to the product. So you lost a little bit, but barely any compared to what the initial concentration of your reactant was. So in other words, if it's almost like you lost no reactant, you could simplify this. You could say, well, let's write this out. So 6.2 times 10 to the power of negative 15 is equal to, we had it before, 2x squared times x over 0.0005 minus 2x squared. We could simplify and say, well, the K value is so small, essentially our reactants are favored, so it's almost like we're not losing any reactant. We are losing some, but barely any. So this value here would be 0. We could assume that the concentration from the beginning for the reactant is going to be roughly the same at equilibrium. There will be some changes, but such small changes that it's almost like we won't even notice it. So we could simplify it to this. 6.2 times 10 to the power of negative 15 is equal to 2x squared times x over 0.0005 squared. We just remove this because the K value is so small, the equilibrium lies to the left where the reactants are, so it's almost like you didn't lose any. There will be a difference, like I said, but so small we barely notice it. And we can make this simplification without it affecting our answers for the other equilibrium concentrations. So it's basically a good enough approximation to use for situations, even when they're simple or when they're very complex. So how do we know when to use this? How do we know when it's safe to make this assumption? What's considered, a small enough K value? So in science, in this particular discipline, there's different rules that you can use. We're going to use the 100 rules. Different labs might use the 500 rule or the 1,000 rule. But essentially what you do is you take your initial value of your initial concentration of your reactant and you divide it by the K value. If this answer is greater than 100, usually we say much greater than 100, but if it's greater than 100, then we can assume that the initial concentration of whatever we're given is going to be equal to the equilibrium concentration. In other words, we can simplify and make the small K approximation to make our lives easier. So for example, in this situation here, I was given the initial concentration. So initial concentration, we'll say concentration initial over K value. So initial concentration was 0.0005 over the K value, which is 6.2 times 10 to the power of negative 15. And when I do that, I get about 8 times 10 to the power of 10. And this is much greater than 100. Since this is much greater than 100, we can simplify by making a small K assumption. So if you plan on simplifying because you don't want to use a quadratic formula or it's just too complicated to find x, you need to show me that you can simplify. You have to justify that. So you need to say, based on my initial over my K, I get a ratio that's much higher than 100. Therefore, I am able to simplify this. And so I'll continue the rest of the problem by simplifying. So let's continue with example 1. We were able to make the assumption. Let's just continue with our process here. So we had said that we had 6.2 times 10 to the power of negative 15 is equal to 2x squared times x over, we removed the minus 2x because we were able to make the assumption, so over 0.0005 squared. And so if we continue this to simplify things a bit, we get 6.2 times 10 to the power of negative 15 is equal to, so 2x squared is 4x squared times x, which is 4x cubed, over 0.0005 squared. We can isolate for x by sending this to the other side and this to the other side as well. So that becomes a division. So essentially we get this. We get 6.2 times 10 to the power of negative 15 times 0.0005 squared over 4 is equal to x cubed. And so now we can do the cube root, cubic root. So that has a little 3 up here because it's not square root, it's the cubic root. And that will give us our x value. So this should be equal to x, which is equal to, so we'll put that in our calculator, so 0.005 squared times 6.2 times 10 to the power of negative 15 divided by 4. Then we'll do our cubed root in your calculator, and we get oops, let me retry that one more time. Usually I like to put my calculator in scientific notation here, in the scientific mode. So 6.2 times 10 to the power of negative 15 times 0.0005 times 0.0005 divided by 4. Let's do the cubic root of our answer there. And then I get about 7.3 times 10 to the power of negative 8 moles per liter. That's our change that's happening. That's our x value. It's so small that if you tried to remove that from the 0.0005 minus 2x, it would barely make a difference. So we found our x value there. So now all we need to do is go and find our final concentration. So we know the concentration of the H2O at equilibrium is about 0.0005 molar because we made that assumption in the because of the small K approximation. So now we need to find the H2 and the O2. And so based on our equilibrium chart, the H2 is 2x and the O2 is x. So this is 2x and this is x. So this would be approximately 7.3 times 10 to the power of negative 8 molar because it's just x. And then this is 2x, so it's 2 times our answer there. So we get 7.3 times 10 to the power of negative 8 times 2, and we get about 1.46 times 10 to the power of negative 7 molar. Or we want this to, let me just double check, I think it was 2 sig figs I wanted. 2 sig figs, our K value is 2 sig figs. So we get about 1.5 times 10 to the power of negative 7 molar. So this is our concentration of H2, this is our O2, and this is roughly our H2O. If you wanted to check it out to see that, this actually made sense, that the approximation is justifiable, if you do 0.005, then do minus your 2 times your 7.3 times 10 to the power of negative 8, you'll get about 0.000499854. So you'll get, so if you tested it out, you get 0.000499854. And when you round this, to 2 sig figs, you get about 0.00050 anyways. So you get the same answer. Your initial is almost the same as your final. It was such a small change, it didn't make a huge difference after all, concentration-wise. So that means that it was truly justifiable to actually do that. So what did we do here? Well, basically, we had an ice table sort of question to do, where you had to set up an ice table with your concentrations and put them in there, find your equilibrium expression um, equations, and then create a equilibrium expression so that you could solve for x. But you'll notice that here it was particularly difficult to solve for x, even if it's not, technically you could do the next few steps anyways, but here it was very difficult to solve for x, so quadratics wouldn't have helped us out very much. So what we had to do here is we had to notice that our k value was very small. And so because it was small, it allowed us to say, well, essentially, we're not really going to lose much of our initial stuff since the k value favors the stuff on the left since it's so small. So to actually justify that numerically, though, what we had to do is we had to do our initial concentration divided by our k. And if that's larger than 100, much larger than 100, then we can make the assumption, the small k approximation, which is the initial concentration is equal to the equilibrium concentration. In other words, this minus 2x will have no effect, or minus x or 3x or whatever it is, will have no effect or very little effect, so we can just kind of cancel it out. And now we have a much nicer denominator to deal with when we're trying to solve for the x. And so since we were able to make that justification, we then went in and continued to solve for x with the justification in place. And it made it nice and easy to find what the x value was over here. And so then we could go plug that x value into our concentration of H2 and O2. And there we have our final concentrations given to us for each of the entities in this equilibrium. So you can use this really anytime as long as you're able to justify using it. And it does make your life a lot easier, especially if you want to just do a quick calculation to see what the equilibrium concentrations are going to be. You can go back and check if any of the other questions that we did in previous notes can use this justification. And if they can, try it out and see if your answers are basically the same to show that justification actually makes sense. So in the next video, we're going to do another example where we may have to use a justification. I recommend you try it yourself first to see if you understand it from the first example, and then afterwards take a look at the video to compare your work to my key and assess yourself.